Alright guys, welcome back to the channel. We're going to be solving question 2 from the chapter 7 of Beer&Johnston textbook Engineering Mechanics. And in this one, we need to determine the internal forces at point J of the structure that we can see. We previously solved the question 678 in this channel. It should be one video right before this one, or if you go to the playlist, you can see the answer for question 678. But the information that we need from that question is that at the end of that question, we did the free body diagram for the entire frame, and we managed to find the reactions that we have at point D, which was dx and dy. And what we found for dx was 900 pounds, and what we found for dy was 750 pounds upward. So in this question, we need to find all the internal forces at J. So we can either go with this section that we have in here or the rest of it, which probably would be more complicated. So just going to break it down or do a section at this point. And I'm going to draw the free body diagram. We have 2D, one of them 900, and the other one 750. And we're going to take a different X and Y in here. So we have different X and Y in this one. We'll see later why I'm choosing a different X and Y is going to help us in the calculation. But let's see what we have in here. So we're going to have a axial force, shearing force, and a moment. And we can just pick one direction for now, and we're going to see what happens after. So our X and Y that we're going to call in this one, it will be a little bit different. So it will be, this will be our X. Maybe we should X prime just to avoid confusion with the X and Y that we had in the previous question. And we are in equilibrium. We're going to use our sum of all forces in X and Y. But this is going to help us to simplify the equations a little bit more. But before that, we need some angles in here. If we see the right triangle in here, we can call this angle alpha, and we can find alpha pretty easy because that alpha is this one in here, and this will be alpha 2. So if you want to find the tangent of alpha, we basically have this right triangle. So we have the opposite 6/16, or our alpha would be tangent inverse of 6/16, which will be 20.56 degrees. So now we can go with our equilibrium equations. Let's start with the moment about point J, since we have the most unknowns at point J. Counterclockwise positive as always. So we have the moment, or the bending moment. So we have the moment of 900 about J. As we can see, it's a clockwise moment, so negative 900 times. So this is the line of action. The distance that we are interested is this distance, or if I show it in here, so we have this right triangle here, and we are interested, and we know this side is 4, and we are interested in this side. We can call it A, but keep in mind that we have this angle now, so it should be easy to find A. Basically, if we go with the tangent of alpha, which was what we found in here, 6/16, in that triangle, the green one that I'm showing in here, we have A over 4. So the A would be 6 times 4 divided by 16, or 24. If we divide them by 8, it will be 3/2, or 1/2. So this will be 1/2. And the next moment is the 750, which is a counterclockwise moment. So plus 750. And the distance would be the line of action we are interested in here, which is what we have in here, or this 4. So we can find the moment now. It will be 900 times 1.5 minus 750 times 4. So the moment will be 750 times 4 minus 1650 pound-foot. And the negative sign shows that the moment is actually clockwise. So our assumption was not correct. Now we can do sum of all forces in x prime equals 0 and same for the y prime. And what we have in x direction, we have minus, we have the 900, but like the angle that we had alpha, here we have alpha 2. And if we look at this one, this angle here is also alpha. So we just have to resolve those into x prime and y prime components. So for that one, we have 900 cosine of our alpha 20.56 degrees minus f. And we also have the x prime component of 750, which will be plus 750 sine of 20.56. So our f basically in here is 900. Let's calculate this. 900 cosine of 20.56 plus 750 times sine of 20.56. So our F would be 1106 pounds. And the angle that we have is the angle alpha, which was what we had in here, 20.6 degrees. That's our F. And our Fy would be, this time we have y component of each, so 750 sine of, cosine of 20.56 minus the y prime component would be negative, so minus 900 sine of 20.56, and we're going to have minus v is equal to 0. Our v is downward, so we can find our v, which will be 750 cosine of 20.56 minus 900 times sine of 20.56. So our V in here would be 386.12, and the angle that we have would be, we can report this angle, which would be 90 minus alpha. So if we show this angle here, will be 90 minus alpha, which was 20.56. So 90 minus 20.56, which is going to be 69.44 degrees. So yeah, that would be the final answer for this question. Again, if we want to go with our normal x and y, we have to break down each of these two x and y components. So that means we have to solve two equations with two unknowns, which would be more complicated than what we did in here. In one shot, our fx gave us, or I should say our fx prime gave us f, and fy prime gave us v. So it's going to save us some time, and solving those two equations will be much harder than this. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next one.